Okay, we're going to start again. This lecture has a fair amount that's related to demand systems, but not directly a demand system stuff. So I'll talk about the pricing equation a lot and its implications. So the topics that I'm going to go are those. I'm going to talk about what are the sources of identification in market level data. So where is it really coming from? And it's going to end up that there's going to be a precision problem most of the time from just market level data. You're trying to estimate a lot from not so much data. Okay? And I'm going to talk about how you can get around the precision problem, how you can confront it, so to speak. And then I'm going to go to the pricing equation, and that's going to be one way of confronting the precision problem. I'll talk about it in some detail, including how you can use it to generate instruments in an optimal way. Optimal is in quotation marks. And then I'm going to talk about the pricing equation more generally, because I think there's been a lot of confusion about hedonic models and their relationship to what we're doing here. Okay? And I'll talk to it also. I'll use as examples the CPI, how you use it in the CPI, and how you would use it in evaluating amenities and things, because it's sort of behind all this, and you might as well see it. It's only a couple minutes. Okay? Okay. So I think the lesson we learned from BLP, I was just saying this before, had we not, so we had 20 years of data. I don't know how good that is. It isn't the 1,000 markets, but it's 20 years of data on the auto industry where we think we have a fair amount of information, okay, because it's an industry that's been studied a lot. And when we just tried to do the demand side alone, okay, we got nowhere. So there would not be a BLP had we stopped there, okay? We got nowhere in the sense that we could get estimates, but they were so imprecise that they weren't going to be usable. Okay, and there's a footnote in the paper to that. Nobody remembers that, but there's a footnote in the paper that had that in it. So, and this is not unusual, because what you're doing is, if it's a national market, okay, you have, however many years you have in the national market, and you have the shares in those markets, shares of different products in those markets, and from those same simple shares, you're trying to get the whole distribution of preferences in the whole community, okay, that you're studying, in this case, the nation. And that's a lot task of just, if there's 50 products, 50 numbers over 10 years, okay? The question is, where is the information coming from, okay? And you can tell a little bit about where you can go this way. There's differences in choice sets across markets and time periods. So what they're doing is if you held the characteristics of the population constant and you added new products and you compared the new product to the old product, say they were the same in all but one characteristic, okay, you would see as the demand moved from one product to the other what the preferences were for that characteristic. So essentially, moving the choice set around, if you could move it wherever you wanted, would trace out the distribution of preferences over characteristics. Okay? That's one source of identification of market level data. The other source of identification is you know something, and this is where the CPS and data sets like that come in. You know something about the demographic features of different markets or different counties if you're going cross-sectional. Okay? So you can see that if you think that the preferences are a function of income and family size and stuff like that, demographics, okay? You see the same choice set in different places, okay? And you see different demographics in the different places. And you see, Greenwich, which has an average income of, something like $200,000 a year, okay? And you compare it to Bridgeport, which has an average income of $30,000 a year, and you see how people at $200,000 care about price relative to people who are $30,000 care about price, okay? So you're tracing out that by moving the demographics around and tracing out the preferences over the same set of characteristics by moving demographics around. Now, you might argue that neither of those are a lot of information, and that's often true, okay? So if you look at national markets, okay, usually there isn't a hell of a lot of variance in demographics over the time periods that you have. The nation's demographic distribution just doesn't change that much, okay? So you're looking at differences in choice sets over time. And in some goods, if you took computers, okay, the difference in characteristics over time, there's a lot of differences in characteristics over time. You'd really be able to trace out a lot. But in autos, you wouldn't, and it would be very hard for you to separate out, when you get a difference in choice set, there are many things that change at the same time. It'd be very hard to separate out the various effects, okay? And that's what was going on in BLP. If you do cross-sectional analysis like Aviv's stuff, okay, the serial stuff, okay? And you fix the choice set, there is quite a bit of variance in the distribution of attributes of demographics across counties, typically. I showed you that in the first lecture. Remember when I showed you? There is really quite a bit of that. You have to worry a little bit. This unobservable, it's everything you don't see, okay? That's what it is. It's like a residual, right? It's not, so it may well be that everything you don't see in one county is different than everything you don't see in another county, okay? And you have to worry about that the preferences, the unobserved part of preferences are differences across counties. That gets even more complicated if you think that, in this case, the manufacturers are putting different products in different counties, because they will put products in that are, that are good for the unobservable characteristics of that county. Okay, so you have to worry a little bit about it. Okay, and then if you're looking at demographics, the problem usually becomes there is a lot of variance in the demographic characteristics, but often there are other factors that determine choice preferences. So if we were doing cars, it would matter very much whether you had a kid who you had to drive to a soccer game, okay, and had to have 10 kids in the car, because then you might want a minivan, okay? Or it would matter very much what your other car was that you could use, okay? And those are things that we don't really observe often in our data sets, okay? So they're going into the unobservables, okay? They're going into the unobservable preferences for one thing or another, okay? And they may have different distributions over counties also, okay? So that can complicate things also. So there are complicating factors. I don't mean to kill all of this. I really don't mean to. But I want to motivate the fact that we want to bring in more sources of information, okay? So there isn't a lot of precision in just market level data, and you want to bring in more sources of information. And there are two ways of doing this. And it's always true in econometrics, okay? If you've got something that's imprecise, you can do one of two things. You can either add data or you can add assumptions, okay? And both of them will make it more precise, okay? So it's not always bad adding assumptions if they're good approximations, okay? So when you can add data, there's many different forms of this. Aviv said, well, what I'm going to do is add many different markets, okay? Which is one way of adding data, at least to BLP, because we just used one national market, okay? The other is to add microdata, okay? So this is my favorite option, okay? But it often isn't available. It's also the most costly thing, okay? And it often isn't available. By the way, when you say, I want to be very clear, everything we do in econometrics, it's an approximation, okay? Nothing's exactly right. And the question isn't, do you get it exactly right? We'll never get it exactly right. The world's too complicated. The question is, do you do it better than the next best alternative? Somebody's going to make decisions on the basis of something. I tell my class this all the time, on the basis of something, and the question is, are you doing it better than that something? Because if you are, you have positive marginal product. So I don't mean to be too negative, okay, on this stuff. And I do it all the time. The real advantage of this class of models and adding microdata, okay, is it's a micro model. Okay, and then we aggregate it up. Aviv did it, and I did it. We aggregate it up. Okay, so there's no new model required. The micro data can be used exactly the same model as the macro data. Okay, and they will be totally consistent with each other. Is that clear? Okay, so what happens in these models is, because of that, one, it makes it much easier to work with. But because of that, in almost all of the markets that people deal with, they have the aggregate data. Market shares, prices, and characteristics are typically easy to get. Is that clear? So when you have microdata, okay, you also typically have aggregate data, product market level data. And so when we discuss this, and I will discuss this, okay, tomorrow, okay, I'm going to show you how to use both of them together. Because you always have them together, and you'll see there are sources of information in the aggregate data that really help you with the microdata. And there's sources of information in the microdata that really help you with the aggregate data, okay? And using them together is the right way to think about it. Okay, so when we do this, we'll use them together. So it comes, by the way, in many different ways, the microdata, and I'll go over a couple of them at least. You know, the one that Aviv showed was Penny's work, Penny Goldberg, which, by the way, was a very nice paper, especially at the time it was written. This was, I should say, maybe you should say, this is her thesis. So this was a student coming out in the market who did this before BLP was published and stuff like that. I mean, it was written before it, so it's quite impressive. I thought I wanted her to come to Yale at the time. Okay. But she used the Consumer Expenditure Survey. This is a survey that underlies the Consumer Price Index. It asks people, you know, what they bought. It's a small survey. It's too small to really, well, to think of using intensively as a microdata source where you actually had people choose a product, okay? Because, you know, for most of the autos that were in, there wasn't anybody who chose it. It was just too small a data set, okay? But you can easily use this kind of data, and Emil Petrin did, to get the covariance, or the correlation, between individual characteristics and household characteristics. So you can see what is the actual correlation between price of the car and the income of the family that bought the car, okay? Or the income of the family that bought a car versus income of families that didn't buy a car. Is that clear? That you can get fairly precisely, and your model has an implication for that. Is that clear? So you can set some of the parameters of the model, but making sure the model's implication is consistent with that data, okay? And I will show you how to do that tomorrow. The other kind of data, by the way, there's also privately generated surveys. A lot of people use this. It's usually from marketing firms. So it's usually from for-profit firms. Is that clear? They usually don't give you the whole data set. Again, they usually just give you the average income of somebody who bought car X or something like that. So it's a very similar kind of way to use it, and I'll show you how to do that tomorrow too. That kind of data, by the way, typically they will not give you current data because they're selling it, okay? And or it's too expensive. They will give it to you if you're willing to pay the right price, okay, which you probably aren't. But they will give you older data that's not useful to them anymore at a very discounted rate frequently. So some of the stuff I show you today will be from that kind of data. Okay, the other kind of data is microdata. And what I call microdata is when you can match an individual to the product the individual purchased. Exactly, okay? It's fairly rare in our industrial organization, but you know, the data, auto data that we're going to use in the micro thing, that has it. The home scan data on which Aviv was, you were using home scan, right?
Not there.
Yeah, it's also microdata. There's more and more of it, and there's actually an increasing amount of it in public finance also, okay? For example, the data on schooling choice actually lists the preferences of schools of different individuals in the Boston and New York system, okay? And that's exactly what you want to know, okay? It's, you know, what was your first choice school? What was your second choice school? Indeed, you'll see later on, okay, that having more than one choice is extremely helpful. It will nail things really very well, okay? So having multiple choices, okay, is yet better, okay? So the KMIP data, the data on the auto industry has first choice, and then they ask the person, if you hadn't bought this car, what car would you have bought? That takes the first car out and looks at what's the closest thing to the first car, which ends up being terrifically informative, and I'll show you how exactly when we get there, okay? Okay, so that's tomorrow. So today I'm going to talk about adding assumptions, okay? There are a number of ways of doing this, but the most prevalent, I think, is to add the pricing equation. We did that, but we did it, you know, because it had been done before many, many times in other ways, okay? So, and it's typically a Nash in prices assumption. Some people call that Bertrand. So every firm is setting their price to maximize their profits, okay? And it's a full information assumption. So I'm setting my price to maximize my profits, and I know what the prices of everybody else are at the time that I'm doing this, okay? To implement that, I'm going to need more assumptions. So I'm going to bring more assumptions to bear on the problem, okay? I'm going to add the Nash assumption, but I also need a cost function. Because prices, the model for prices depends on the demand system, but also depends on the cost function. Okay, so I'm going to have to bring in a cost function. But the thing that's going to happen is the pricing equation. What's going to happen is now you have a demand equation for each good, right? So you have J right-hand side variables, the number of goods. Is that clear? That you have stuff on the J left-hand side variables, and you have stuff. Okay, so the pricing equation is going to double the number of left-hand side variables because there's one for each product. Okay, and that's the source of the initial information. You're going to have to also increase the number of parameters because you've got to get the cost parameters. Is that clear? But the cost parameters, you're going to play the same trick that you played in the demand system. You're going to say there's J products, but there's a small number of characteristics that have to be costed out. Okay, it's going to be the same X's that are on top and maybe some wage variables and rental variables. But it's going to be much smaller than J. Okay, and that's the source that's going to come in to help you. So I should say a couple of things. The assumption of Nash and prices is an assumption which you can easily argue against. Okay, so just from a theoretical point of view, you can look at models where either demand or cost is dynamic for one reason or another. So cost could be dynamic because demand could be dynamic because it's a durable good. So if we sell a lot of Fords today, the demand for Fords tomorrow is going to be less, okay? Because you just did your okay. So it could be a durable good. It could be what's called an experience good because I've tasted the product or tried it. I've changed my preferences. And because I know about the product now, it could be a network good like computers. There are lots of reasons why the pricing, the static Nash pricing assumption might be wrong. But the truth is, there is no model in almost any of economics that fits better than the static Nash pricing model, even where it shouldn't fit. Okay? And I'm going to show you some numbers afterwards. Okay? It's an incredibly good approximation. I'm going to show you that for TVs, you get R-squares on the order of 0.95, 0.96. If you were I tell my class this, okay, if you were a labor economist and you were doing a wage equation and you got an R-squared of 0.3, doesn't matter what was on the right-hand side, you get an article in the JP. Because 0.3 is just huge in those stuff, okay? And here we're getting 0.9, 0.95. We know it's wrong, so there's some sense in which you should be careful, okay? But just the fact that the fit is so good is going to end up being very, very helpful, okay, in the estimation algorithm. Okay. Okay. So the pricing equation, and we're going to get to it in more detail because we're going to try and use it for hedonics and things like that and show you what it is. Okay. It essentially amounts to price equals marginal cost plus a markup term. Okay. The markup term, okay, if you just did single unit pricing. So there was this question last to Aviv. Okay. So the markup term is the inverse of the semi-elasticity of demand in the simple model. Is that clear? That's telling you that if our pricing assumption is anywhere near right, the prices there's a lot of information on the demand system in the pricing equation because it's about the semi-elasticity of demand, which is one of the major parameters in the demand system. Okay? And this is what the information content that we're bringing to bear on the problem. Okay? So what's in this equation? You're going to have the marginal cost. Okay? So the marginal cost is going to be a function of the same x's typically that are in the demand system. So if I have a larger car, it's going to cost more. Have a higher motor, it's going to cost, bigger MPG, it's going to cost more. Stuff like that. Okay? And those things will be in the demand system. Okay? And maybe interacted, hopefully interacted with some determinants of costs. Okay? In the car industry, the biggest determinant of cost is exchange rates, but which doesn't sound like a cost, but it is. Okay, so that's one aspect of this equation for price. And what else does it depend upon? Why does it fit so well? First of all, that fits well, right? Why do you know that fits well? Because that's why people did hedonic regressions. They did hedonic regressions because they regressed price on characteristics and they got high R-squares, and then they decided, well, we should use that. So from before me, with Court and Grillakes and all these guys, that at some level these things are fitting, okay? But even if you just had that, but what are we adding to that? We're adding a markup term. The markup term just says a few things very clearly. It says, if the car or if the product is in a very crowded part of the market, so there are many cars that have the same characteristics of this car, is that clear? Then if I increase my price a little bit, a lot of people are going to leave. Because there are cars that are very similar that are right next door. And that's what the demand system will tell you. What's the degree of similarity? Okay? So that's one thing that goes into the markup term. The other two things that go into the markup term is cars that are very pricey. Okay? they're going to be bought by people with high income, okay, who don't care much about price. High income people don't care much about price, and they're going to be not very elastic, which is going to generate high markups, okay, which is exactly what generates the investment in the sunk cost to develop these cars, okay? So the economic intuition in these things is very clear, okay? And then the third thing that goes into this markup term is when there's multi-product firms, okay, and I own 2 products, okay, instead of 1 product, okay? When I increase my price a little bit, when I own the 2, what's the pricing equation? It says I increase my price a little bit, you know, epsilon, okay? I lose some people, you know, I lose some people, that's the loss, and I gain the markup on the people who stick around. Okay, and I keep on increasing the price until that's 0. So the, you know, one balances the other. Okay, that's the Nash pricing equation. Okay, so now what's going to happen is I increase my price a little bit. Okay, I lose those people, but some of them go to my other product that I own because I own the second product now. Is that clear? So the markup, so they earn some of the money back, which means we can push prices up farther. So the other thing that will go into this markup equation is the amount of other products I own and how close they are to this product, which also comes out cleanly in the data, okay? So it may be that we don't have the exact form right, maybe more dynamic and everything else, is that clear? But the intuition is very strong, and even if it was wrong, I'll show you there are senses in which it can help us very much, okay, as we go along. Okay. Okay. So I'm going to now go through just what the pricing equation is. I've even went through part of this, but I guess I have to build it up. So I'm going to do it for a multi-product firm because typically the markets, each firm owns many products in the markets we study. And I'm going to assume Nash prices, though you can do other things, and Aviv talked a little bit about other things. I don't need, you can bring, the Nash pricing assumption works well, usually. Okay, it may not work, works well as a predictor, at least, of price. Okay, it may not be the right thing to interpret as a causal thing, but it works well as a predictor for price. Okay, but you could do other things. If you had other things like collusion, you maximize the profits of these 2 firms together. Okay, you thought that was happening, you could bring a pricing equation for that to bear on the problem instead of what I'm going to do. Okay, any pricing assumption you could replace this with. Okay. We need 2 assumptions to get going. We need an assumption on the nature of equilibrium and an assumption on the cost function. So the cost function, the typical assumption, is that marginal cost is a function of these observable W's, maybe the quantity if there's increasing or decreasing costs, okay, and an omega term. So the omega term is the analog of the Xi term in the demand system. It's whatever affects cost, which isn't in the W's. Is that clear? It's the unobservable component of the cost system. So it could be productivity. It could be, remember, the Xi is missing from this term. So if Xi is really quality, you might think quality costs something. Is that clear? So the omega would be large for large Xi firms, Xi products. So you would want the Xi and the omega to allow them to be correlated. Okay? Okay, so the advantage of this, okay, I'm now going to have, remember, I'm going to have J more left-hand side variables, and you want the W's, which are the observables, to be, they're presumably the number of parameters you're going to estimate must be less than J by a lot. That's what's helping you in this. If I had another parameter to estimate for every cost, okay, I'd be in trouble, okay? So we're adding degrees of freedom. And the other thing you should realize about this equation is that Q, which is quantity, that's a function of both. So omega is a function of Xi, okay? So anything that's a function of Xi is correlated with omega, okay? In addition, okay, so Q should be correlated with omega. Also, lower marginal cost firms should have a lower price and sell more, okay? So there's an endogeneity issue with Q just like there was with P, okay? So I should note, a lot of what people do is they write down this function and then, sort of modify it a little bit to account for factors of the market that aren't accounted for well in this this model. Okay, so for example, the exchange rate thing. When we did exchange rates, we just put the exchange rate on the right-hand side of the equation. Okay, which is not quite right, right? Because I know exactly the exchange rates, I know exactly the cost, so I shouldn't need to estimate a parameter on that separately. Is that clear? The reason we did it is because, and people do this kind of thing all the time, it's because we know there's also this phenomenon called exchange rate pass-through where it's not passed through immediately. Okay, so we didn't want to force it to be a one coefficient. So that's like an example of how you would fix this up to modify it to fit the market better. So it's not quite kosher, but makes sense. Okay. So what's the pricing equation? I'm going to let JF, I'm going to assume gamma Q equals 0. If not, I need an instrument for Q. So I'm going to assume constant marginal cost. Okay. If not, I need an instrument for Q. So what the firm is going to end up doing is he's going to set, he owns the products in JF. So JF is just a subset of the whole products. They're the products owned by firm F. Okay? So now what it's doing is it's choosing price to maximize the sum of its profits. Okay? So it not only takes into account the impact of the price of this good on the profits from this good, but it takes into account the price of this good on the profits of the other goods that it owns. Okay? So that's what's going on. So, and if you write down the first order condition for that, you get this equation, okay? So again, let me just come back. If this is one good, everybody's seen this before, but just this answers the question before. If there was just one product, it would be price. If every firm owned one product, you'd have the familiar pricing equation. Price equals marginal cost plus the inverse of the semi-elasticity of demand. That's the markup. Yeah? The first equation? This one? Yeah, it should be capital M. Sorry, that's a typo. The M's drop out. Sorry. Okay, that's an error. By the way, there's probably more errors than that. Though I got to admit, somebody looked over these things and was supposed to pick up these errors. But I won't say who. Price equals marginal cost plus a markup. If we had two products of the firm, so you get price equals marginal cost plus a markup, and then you get this additional term, which is exactly what I told you before. It depends on if my price goes up, I lose certain people. The question is, how many of those people go to the second good that I own? And this is the markup on the second good that I own. So this is just the formalities of what I finished talking through you before. Okay? And this markup and this equation here, you can have as many products as you want. Of course, so the intuition before is not quite right. So I should be a little careful here on two things, two counts. Okay, one is if you were going to use this stuff to do a counterfactual. Okay, so you estimated the thing, there was a tax, or there was a policy change, or there was a merger, and you want to do a counterfactual. There are sort of two issues that you should realize. One issue that you should realize is that, if I increase my price a little bit, okay? So if I merge and increase my price in response to that, everybody else's first order condition no longer holds. Because everybody else's first order condition depends on my prices too. Is that clear? So there's really an equilibrium response, and you have to solve for a whole new equilibrium. So that's true. The second thing is, you might think that that would screw up estimation. In fact, it doesn't. Because there is a situation. These are typically simultaneous move games. Everybody moves at the same time, okay? And there often can be multiple equilibria to simultaneous move games. So if you go high, it might be optimal for me to go high, and if you go low, it's optimal for me to go low. So multiple equilibria. The estimation, though, it only relies on the first order condition, which should be true in any equilibria. So the estimation doesn't depend on the multiplicity issue. It's correct, it just doesn't matter which equilibria is selected, how we got to it. Is that clear? What will matter is if I'm starting to do counterfactuals, so if I'm saying what will be the price after they merge, or what will be the price after, so then the counterfactual depends on which equilibria you select. Is that clear? So you can put on restrictions on the equilibria, and I'm not going to go there. There are different ways of doing that. But you should be aware of the fact that if you start using this for counterfactuals, this problem can emerge. Okay? Okay. So there are other pricing assumptions except for that one. Aviv talked to you a bit about them. I'm going to skip that. So let me just give you the details of how this works. And now I'm going back to Aviv's first lecture. Okay? So Aviv taught you how to use BLP, or this kind of estimation algorithm, from just demand data. Now I'm adding a different source of data, and I want to tell you how I'm going to modify the estimation algorithm to take account of this source of data. Okay? So that's where I'm headed. Okay? So I'm going to define this matrix delta, which is this matrix Aviv did define last lecture, which is DSI dpj. So it's the amount that the demand for the other good goes up if the price of this good goes up. Okay? If the other good and this good are both my goods. Okay? So I look for all the goods that belong to this firm, okay? And I put on this row of delta, okay? I put on DSI, dpj for all of those goods, okay? Which I can get from the demand system, okay? And then for all the goods that don't belong to me, I don't care about them, okay? So the DSI, dpj I just said is 0. The delta is 0 for those goods, okay? So if you just rewrite this pricing equation in matrix form, and this pricing equation in matrix form, you get S, the vector of shares, times the vector of prices minus the vector of marginal cost times delta equals 0. Okay? You can believe me, it's just a matter of putting things in the right place and doing it right, okay? Okay, so that just says P minus delta inverse S equals the marginal cost. I just switching sides, okay? Take delta inverse over here, okay? So it's P minus delta inverse S equals marginal cost, okay? Okay, so, and marginal cost just equals W prime gamma and omega, okay? So what did Aviv do? What Aviv did when he was doing the estimation algorithm, he said, look, there's this unobservable demand parameter, demand factor, Xi. I'm going to show you how to solve for it through the contraction mapping in BLP, okay? And once I have this unobservable demand thing, which is this Xi, it's a function of theta, right? Because I'm going to do the inverse. The shares are a function of theta, so the inverse will be a function of theta. So Xi will be a function of theta. And all I'm going to do is I'm going to say, okay, there are some things which are orthogonal to Xi. There are our instruments, okay? And I'm going to interact the instruments with Xi, form an average over products, or maybe over products and markets, and choose the theta that makes that as close as possible to 0, because that's what an instrument's supposed to do. Okay? So that's one way of explaining the BLP algorithm, okay? The hard part is getting Xi as a function of theta, and that's because Xi is in the demand function in a nonlinear way. Okay, you're used to doing instrumental variables where it's linear. Okay, it's not linear. So what BLP had to do is they had to find a transform of the shares that made it linear. So you could then do instruments. Okay, that's what was going on, okay? Okay, so now what I'm going to do is I'm going to find a transform of the pricing function that's linear in the unobservable in the pricing function, and add instruments to, and do instruments against that, and makes them equal to 0. Okay? So once I add Xi, I had J X's, I averaged them, I hit them with an instrument, okay? I got them, I found the theta makes them 0. Now I'm going to say, well, log P minus delta inverse S, that's marginal cost. Marginal cost is W prime gamma plus omega. Omega is the error. So I can say, okay, what if this is the true, whatever the theta is that went here, is the true theta, and this is the true gamma, this is the true omega. Okay? And at theta equals theta naught, the covariance of that with the instrument better be 0. Okay? And that's exactly the same thing we did on the demand side, only now it's a little bit easier, at least if you know delta. Delta is the hard part. Okay? Okay. So all we're going to do is add to what Aviv told you another set of moments, okay, which are the instruments interacted with omega instead of the instruments interacted with Xi. Okay? So get a double, if you use exactly the same moments, get just double the amount of moments you're using. Same instruments, it's double the amount of moments. Okay. So how much have we complicated the estimation algorithm? Okay. So the first time, every time we wanted to evaluate a theta, we first simulated shares and then did the contraction mapping to get Xi out. Okay? So now we got to do that. And in addition, after we get Xi out, we have to calculate all the first derivatives with respect to S, okay, to get the delta matrix. Okay? That's the additional thing, okay? And then everything else is just standard method moments after that. So the only difference is that, okay? So that's how you add the pricing equation, okay? That was my second goal in this thing, okay? So again, you should note that you're adding the pricing equation to the other equations. You're actually adding assumptions, okay? So if you can get away without it, you like to not add assumptions, maybe test the assumptions, but not add them if you can get along without it, okay? But the truth is the pricing equation often provides a lot of information, whether or not it's exactly right, okay? And as you will, and the other thing about it is, we do this for a reason. So you're doing all this demand stuff, and then because you want to do something afterwards, okay? You want to reevaluate a merger, you want to find out a price index, you want to do something with the stuff afterwards. And many of the things that you end up doing afterwards will require the pricing equation anyway, okay? So if you do a merger analysis and you're interested in what's going to be the effect of the merger on prices, you're going to use a pricing assumption whether you like it or not, okay? Because you have to figure out what the effect is going to be on prices, okay? So in that respect, there are sort of three kinds of problems. There are the problems where you don't need to recompute, where I'm interested in doing something which doesn't need to recompute prices at all, okay? There, putting on the pricing assumption might be costly, okay? Because if you screwed up, okay, you're going to get, okay? And the biggest one for that are things like estimating consumer surplus from something, because it's just, you see the prices once, you see the prices in the products again, you calculate the consumer surplus difference, there's no necessary new equilibrium in prices needed, okay? There's stuff, and then there's stuff where the whole interest is in the new equilibrium in prices, like mergers, often, okay? And then there's stuff in the middle, like you put on a voluntary export restraint, which is something we did in one of our papers, and or you put on a tax on gas, and you want to see what happens to the miles per gallon of the new car fleet, okay? And that's going to have a tax on gas is going to also affect prices, but you might think it's second order, and that you would worry less about it in that context. And in a context where I'm really interested in the price effects, my whole policy decision is going to be based on the price effects, which is the case, not totally the case, but almost totally the case with mergers, okay? Or at least it's the claim that that's totally the case. So sometimes you're going to need it anyway, whether you like it or not, okay? So I want to talk now, the pricing equation and the choice of instruments. I want to talk a little bit, Aviv talked about the instruments, he didn't talk about this part of it, left it on purpose to me, he told me he was going to leave this one to me. So I'm going to talk a little bit. Yeah, go ahead, shoot, questions. I'm happy with questions.
So I hear the opinion that if you are able to estimate the demand without using the pricing equation, and that kind of estimate seems to be, you're not adding assumptions, and then you can do the pricing equation for the counterfactual, but people seem to feel more comfortable with that approach.
Yeah, if I could do, so I think what I would do if I had my druthers, and usually like BLP we didn't, we tried and we couldn't get anywhere, okay, is I would estimate the demand equation alone and then the demand equation and the pricing equation, okay, and I would see if they change dramatically, the coefficients themselves. I would try and do a test to see if they're the same, the coefficients changed or not. If they didn't, I would use the added precision of the pricing model, okay. Well, what happened in BLP is you had no precision before you put in the pricing model, so you'd accept anything, okay. I mean,
They differ quite a bit.
so then you have to, and you're trying to do a pricing analysis. So you have a real question of further exploration. Well, they might be different before, but wouldn't be, either you're assuming they were different before, but they won't be different afterwards. Is that clear? Or you're giving me another thing that will happen afterwards, because you need some sort of model which will set prices if you're going to find out price effects. Okay? Okay. Go.
It's all about differentiated products. When you talk about marketing or advertising, conceptually, it's not easy to say on the advertising equation cost per advertising refers to what a condition.
Right.
But has anyone worked out empirically such a model?
So it's, I think I'm going to talk a little bit about this in the third, but let me just say, I mean, you know as much about this as me, but I would just say for the general, advertising, people will often put it in as a right-hand side variable in this model. There's a real question if that makes sense, okay? Because the question with advertising is largely, what's it doing? Is it changing my preferences? Is it changing my choice set? And a lot of the issues that have to do with advertising, you know this as well as I, have to do with that, okay? There's been a little bit of work trying to distinguish that, but not a lot. The amount of work on advertising, by the way, is very disappointing, I think, in IO. Advertising is, just in manufacturing industry, is as large a proportion of costs as R&D, and there's tons more. And if you look at other industries that aren't manufacturing, it's much more. Okay, and we know very little about it, and it's part of the FTC's mission statement to worry about deceptive advertising, and we regulate it a lot, and we do a lot of things, and we know very little about it. One would hope that with these new techniques you'd learn a little bit more, but there really hasn't been much work on that. You had a second question. Oh yeah, let me just say, Aviv and I, okay. So there was this question of whether, in Aviv's talk and in my talk earlier, there was this question whether Xi and X are really independent, or really mean independent. Is that clear? Whether the unobservables are really independent of X, okay? I can talk about that. The answer, Aviv actually answered the same answer I would give, so there's really not much reason for me to say. But if they aren't, what I need is a choice function for X, as well as a choice function for price. Okay, so in the same thing with advertising. And there's nothing that's saying I can't do that, okay? The reason we just aren't there yet. Then you need, typically what happens, at least in autos where we worked, the X's are characteristics of the product. At some level, they're chosen by the firm. Is that clear? Just like the price is chosen, okay? They're chosen, though, before, typically it takes, at least in autos. By the way, this isn't true of all products. So if you looked at chips, okay? The characteristics of chips in the market change faster than the characteristics of the prices of the chip. They'll typically put a new chip in at an old price, okay? So Chris Nosko's thesis, you could see exactly, their big response, the quick response, was the chip CPU, up to a maximum. There was always a maximum for any given technology. There's a maximum. But something happened by a competitor. The first thing that moved was not price, but it was the CPUs that they were going to compete against. Okay? So it's not always true that, as in the auto industry, typically what you think of as you set characteristics, it takes 3 or 4 years. Actually, in the minivan case, which we'll get to, it took 8 years, okay, before the auto industry responds to a change in the environment by putting a new car on the market. They respond first, okay, by putting a car on the market that they like. In the minivan case, it took 8 years, okay? So, the characteristics are sort of fixed for a longish period of time, okay? And the X's are moving around as people's perceptions of the car quality changes, and other car qualities competing with it change, okay? So you think that they're moving more and price is moving more, and they respond with price changes. So you worry about C being related to price more than you relate it to X, okay? And again, there are industries, I know there are industries where that's not correct, okay? But that's this first thing. If you wanted, in that context, if you wanted to do X, you really need a more dynamic model. You need a more forward-looking model, because the thing's not going to get on the market for 4 or 5 years. So they're not doing it in response to demand today. They know that they're doing it in response to many years forward. So when we got the micro data from GM, this is stories, and I'll stop it after this, okay? One of the questions they asked us was, what would happen if we put in a high-end SUV? Okay, because nobody at the time had a high-end, the highest-end SUV at the time was a Ford Explorer, okay? And so we gave them answers, and actually I'll show you the answers we gave them, okay? And we said, look, this is what happens if nobody else puts in another high-end SUV, okay? But in the truth, if you look between 1993 and now, every major car company has put in a high-end SUV because there was nobody there, which meant that there were markups to be earned. Because there was nobody beside it, it was a place where huge markups could be earned. So, I don't know a car company that doesn't have, even a part of a car company that doesn't have a high-end SUV now. So our predictions, we told them, we predicted it would kill the market. You do just terrifically well. And they would have, had there not been a Mercedes SUV, a Porsche Cayenne, a Lincoln Navigator, and once you put that in, the game's over. Okay?
That actually leads to, I was thinking about what you said. You explained that the proton match looked pretty good.
Yeah.
So you can think of the thought experiment, which actually you just described, which is start with a
So it's not so so let me just, so this is one of the problems with BLP. What happens in BLP is it can't blow up. The prices can't get too close to each other. The cost-price elasticities can't get, that's what the epsilons do. Okay? So you might not, that's the thing, that's why I pushed you on the pure characteristic model. That's exactly the case that BLP doesn't work well for. Okay? I should probably go on with this lecture. So, okay, so I'm going to derive the optimal instrument. So there is, in fact, an optimal instrument formula. Okay? So the question is, if I was going to instrument for, I'm going to use instruments. Okay? The question is, and I say xi and omega, or just xi, whatever you like, is mean independent of these variables. Is that clear? There is exactly an optimal instrument formula that's due to Gary Chamberlain. Okay? And all I have to do is translate it, okay, to this context. Okay, so I'm going to do that for you now. Okay? But let me say before I do it, why doesn't everybody do this? Actually, we did do it, okay, and the new work, there's a lot of new work doing it. We didn't do it in BLP, we figured it out afterwards, okay? But you're going to have to, the optimal instrument formula, it's going to depend on the pricing assumption, right? Because I need instrument for prices, so that it's going to be, it'll have to depend on the model for the pricing assumption. Is that clear? Okay. So again, and then the second thing is, so it's going to depend on that assumption. Okay, and the second thing is, it's going to generate an instrument which is hard to compute. Okay? Now, let me tell you, this is a sense in which that's overstating the problem. Okay? Because it's not, what happens with the optimal instrument formula, and this is true for all instrumental variable things. If you have a right-hand side variable which you have to instrument, is that clear? And you want to find the optimal instrument, I can give you the formula for the optimal instrument. Okay? Now, it depends on how that right-hand side variable is set, because it's going to depend on the model for the right-hand side variable in order to get the instrument. Okay? Now, the model, but the good thing about it is if the model is slightly wrong, it doesn't matter. You still get a consistent estimator, because it's just going to be a function of the same x's, all the x's which are exogenous. So you're going to get a consistent estimator, and the extent which you'll be farther away from the optimal instrument is just on how close the prediction is from your model to the prediction that would come from the optimal instrument. Okay, it's just the correlation between those two things. Okay, so we're in good shape with prices. Okay, you might not believe the pricing formula, but it really doesn't matter. We're going to make it as a function of things which are exogenous, if you believe the exogeneity assumption. Is that clear? And we know it fits well from what I just told you before. Okay? So using the optimal instrument formula makes a lot of sense in a lot of these cases. So what did I say? I said, even if the pricing assumption is wrong, it's still going to give you a consistent and pretty nearly optimal estimate. Okay? At least in the pricing case. Okay. So this is just me mimicking Gary Chamberlain's paper. Okay? So there's nothing new in this from my point of view. Okay? So I'm going to foreshadow the notation. I'm going to just do it with xi. So I have, what's my assumption? My assumption is that the expectation of xi given x and w is 0. Okay, it's mean independent. Xi is these are my instruments, x and w. Okay, so Gary's formula, so that's my assumption. And beta 0 and beta u, those are the two sets of betas. One is on the delta, from the delta term, and one is from the, this is his theta, this is Aviv's theta. We tried to get this all together. We spent a day together trying to get notation together and stuff, and we never quite made it. So, and we actually talk the same language, so people who don't talk the same language have a lot of trouble with this notation. At least we knew each other were talking about. But so you'll have to excuse the fact that notation isn't together. So that's it. And what's the optimal instrument formula? What it says is, look, I'm going to take the expectation of this xi, given x and w, okay? And then I'm going to take the derivative of it with respect to beta, the parameter I want to estimate. Okay? Okay. So, and that's going to be my instrument for the x that beta is on, for the beta that I'm going to get. Okay, for that particular beta. So again, if I have k betas, I have k instruments, exactly the same amount of instruments as parameters I want to estimate, which makes it easy. Not a ton of instruments, just exactly the same amount is the optimal instrument formula. Okay? Okay. You know, as just a conceptual issue, this is actually a pretty hard problem because this says that any function of x and w can be an instrument. So I could have infinite numbers of instruments. Okay? And I could keep on adding these things, and maybe you would expect to do better. And Gary's formula says, no, you can't do better than more than one instrument per parameter. And this is the instrument. Okay? Better in the sense of the variance-covariance matrix. They're all consistent, okay? But a better variance-covariance matrix, okay? Just like, okay. So this is the formula. For each beta, I take the expectation of this thing, of the derivative with respect to beta, which is in saying the expectation is a linear operator, and so as a derivative, I can take the derivative inside and then just take the expectation of it. Okay. Where this delta here is the delta we get by inverting the shares that Aviv told you how to get. Okay? And this formula has to be evaluated at beta equal beta naught, at the true beta. Okay? To get the optimal one. Okay? Okay. So let me just tell you what the instruments are. Okay? And you'll see what they are. Okay? So if for an x in the projection of delta on x and p, everybody with me? Those x's. Remember, we project the deltas onto x and p, and then there's the theta. Okay, it's just x itself. So the instrument is x, because it's exogenous, and nothing, it's independent of the error, and nothing matches up with x better than x. Okay, so it's its own instrument. Okay, for the price in the delta projection on x and price, okay, it's the expectation of price given x and w. Okay? So that's where the problem comes in, okay? Because that expectation may be hard to do, okay? So if you think of what's going on, even if you assume Nash prices, the expectation has to be over the c and omega that I could have for every xw. Okay, so it's a bit of a mess, okay? Okay? And for the beta u, it's just the derivative of delta with respect to x and w. Okay? So you have you've computed the delta, and you can just see, you can just take the first, you can do it numerically. You can just take a perturbation either side and take, the differences and divide it by 2, and you get a numerical measure of the derivative. Okay? So if you were going to do this, there are two things that you have to fix. Okay? One is the betas depend on the true value of the parameter. I don't know those. So essentially, I would convert to a two-step estimator. I would do something simple first to get an idea of what the right values are, and then use those values to compute the instruments and redo it. Okay? So that it's a little bit harder. You have to do it twice. Okay? Again, the hardness of these problems with modern computing, we were talking about this in the break. The hardness is not the computational hardness. Maybe I know the guys who do MPEC and everything think it is. But computers are pretty good now for most of the problems. The hardness is writing the programs and getting them right without any errors in the programs. Okay, so if once you have the program ready, doing a little more complicated model isn't such a deal with the computers that we have today. Okay. I should say that it's a two-step estimator. For those of you who know some econometrics, two-step estimators, you usually have to account doing the variance in the first step, for the error in the first step estimator of beta naught. This is what's called an adaptive estimator, so that error won't affect. You can just pretend that you got it exactly right on the first stage, and you'll get the right variance-covariance matrix. I'm not going to prove that, but it happens to be true. Okay? So that eases things a little bit. Okay? Okay, so now the question is, so the two steps, okay, help you get around the beta 0, getting the betas. Okay? But I still have to be able to compute EP given XW and E of this given XW. Okay? So this, I told you how to do. You're just going to do derivatives. Okay? The problem with P is it's an equilibrium object. Okay? So to calculate its expectation is pretty hard. I'd have to draw x's and omegas for everybody and recompute equilibria every time and then integrate out. Okay? So one thing we did but again, I'm going to go back to this thing. As long as it's only a function of x and w, it's going to be a consistent instrument. And all I really want to do is get it close to the optimal instrument, because the closer I get, the more efficient my estimator is. Okay? So what we did in this AR paper on voluntary export restraints is we said, okay, look at the first order condition, put C and omega equals 0, which is their mean and median, and just calculate what the optimal instrument would be if C and omega were 0. That's easy. You just look at the first order condition, plug in zeros for C and omega, and ask what's the, 0. So it's not a function of C and omega anymore. What's that number? That's going to be my instrument. Okay? There's a bunch of papers on this now, by the way, on doing this different ways. There's this new paper by Verboten, and I guess it's one of his students, where they do it slightly more differently. They estimate the C and omega in the first time, and then they take random draws from the distribution of C and omega and compute an average of the derivative, the average of the prices that they get from the equilibrium by putting in the random draws. Okay. They have extensive simulation results, Monte Carlo results on performance, and they really like the optimal instrument. So I hesitate to say that either us or the way they do it. Actually, I like the way they do it better. This goes back to one of Aviv's comments. Every time I see a Monte Carlo experiment of something that somebody introduced, the thing that he introduced always wins. So you can have a little bit of problems with that. The problem with Monte Carlos, by the way, is you have to decide where the characteristics are and things like that. And it's not like you can draw randomly, because again, they're choices by products. There's logic to them in the market. And you can't just take random draws and say, these are the products, and then, because that won't mimic what happens in real markets. Okay? So it's actually pretty hard to do a good Monte Carlo. But I don't want to knock it. They did a lot of it. Okay? And they come out with this really winning, especially theirs. Okay. So that's what I was going to say. I'm going to spend the next half hour on hedonic functions and price indexes. Okay? I do this for two reasons. One, the hedonic function is used all over, and I think often misinterpreted. Okay, so, and seeing we've just went over the pricing equation, I can tell you exactly how it's misinterpreted. Okay? And the second thing is that one of the applications of all of this stuff is in doing price indexes, like the consumer price index. So I'm going to show you the relationship between the stuff we're doing now and the consumer price index and how they use it. So the consumer price index, again, it's another application. It should be, in principle, an application of demand system analysis. Okay? Because I will show you exactly what it should be right now. Okay? So I'll first of all introduce the consumer price index, then I'll introduce the hedonic pricing equation. Okay? And just show you what's going on and how to use it and how not to use it. And then I'll show you how hedonics can help you fix the consumer price index. Okay? So I'm going to do all that in a half an hour. That should be lots of time to do it. Okay. So I'm going to do the CPI. You could do also the PPI or whatever you like. So let me remind you what the consumer price index is. It's the cost of reaching a certain level of utility. Okay? So this is the expenditure, or the minimum expenditure, on these goods Q, okay, for this individual with characteristics Zi to reach utility U bar. Okay? That's called the expenditure function. Somewhere in your graduate or undergraduate days you saw that. Okay? And so it implies that the expenditure function is a function of the choice set, the characteristics of the products that are there, your characteristics, and the utility you're evaluating it at. What utility do I have to get to in the expenditure function? Okay. So what the CPI is supposed to be, okay, is it's supposed to be, I'm going to look at a Lasper's index. This is called Lasper's index. And it says, okay, how much money do I have to give you today, okay, to give you the same utility you got yesterday? Okay, so you have EI0 was what you spent on goods yesterday, and you got utility U bar. Is that clear? So what I want to know is how much money do I have to give you today? The choice set has changed. The prices of goods have changed, and the goods have changed. The characteristics of goods have changed. Okay, how much money do I have to give you today, in addition to what you spent yesterday? Okay, to get to or maybe less than what I spent yesterday, in order to get you to the same level of utility you had yesterday. That's what the CPI is supposed to be. That's called the ideal price index. Okay. Now the question is, how do they do the CPI? Okay. And how they do the CPI is very simple. They take the weights of particular goods in the consumer expenditure survey from a particular year. Is that clear? So the consumer expenditure survey is the same thing that Aviv was talking about. And the reason we have a consumer expenditure survey is to have a CPI. Okay? So what they're doing is they're sampling people and seeing what they buy. And it's a random sample of people. Okay? And so what we do is we take a base period weight of the goods they bought, okay, what they bought in the base period, okay, and we figure out how much it costs in the base period and how much it costs to buy that same bundle of goods, okay, in the comparison period. And that ratio is called the match model CPI, okay. So the expenditure groups are things like computers and TVs, and they have a random. First of all, they have a random sample of people and what they buy, and then they have a random sample of places that they buy them. Okay? And the way they get the prices is they send what's called data enumerators to these stores. Okay? And they give them a bunch of characteristics, and they say, find something with that characteristic, what's its price? Okay? And the guy writes down the price and the characteristics so he knows what to come back for. Okay? And then he goes back in 2 months, writes down another price. Is that clear? Okay. Takes the ratio of those prices for a bunch of TVs in a bunch of cities. Okay. And that's called, each one is called a price relative. They average the price relatives for TV and then put a weight on TV. Okay. And that's how they get that's how they construct the price index. Actually, that's not quite right. That's how they used to construct the price index. Okay. They've now gotten better than that. But okay. So what's going on? Why is that a reasonable thing to do? Well, it's a reasonable thing to do because, remember, these are mostly they was started for entitlement programs. Okay? So they were worried about people having a certain minimal level of standard of living. Okay? So what would happen is this is a very simple thing to do. Okay? And we know that if we give you enough money to buy the same goods you bought yesterday today, you can do at least as well as you did yesterday because the prices have changed and you might be able to improve on that. But we've insured you your entitlement. Okay? That's where it started. Okay? And this just goes back to a Russian economist called Konyas, okay, who actually started this out. Okay? So there was a big debate in the United States. You guys probably don't remember this, but when I was in school, this was a big debate about what the CPI. Actually, this all started because you guys know who Alan Greenspan was, or are you too young for that? Alan Greenspan, everybody knows who Alan Greenspan is. So Alan Greenspan decided that the CPI was overestimating the rate of inflation, okay? And indeed, like I said in the first lecture, if it was overestimating by 1% a year, we could kill the budget deficit, okay? And so we should set up a commission you wouldn't believe how pervasive use of the CPI is, okay? So it's all tax brackets are indexed to the CPI, okay? Every entitlement program in the country is indexed with the CPI. Every government wage is indexed by the CPI. It's just a number, and a lot of private contracts are also indexed to the CPI, okay? So it goes on forever. So it's a big number, okay? You change it a little bit, it changes the economy, okay? By the way, what happened started interesting, which is he had this commission called the Boston Commission. By the way, this is how I got into this. I was asked to testify before the Senate Finance Committee on this, which got me interested in the question. I was the young guy. Everybody else was old. I was younger then, and everybody else was older than me. But this Boston Commission was headed by Boston, and they went out and sort of waved their hands a bit and said, okay, here's the biases. They're 0.4% because of substitution bias. So substitution bias is that, it overestimates. So they came up with a number of 1.1% or 1.2%, something like that, that it was overestimated every year. That's a big number. Okay, because the CPI is usually rate of inflation. At those times it was about 3%, so it was a third of the CPI. So it was a third of the adjustment every year, okay? So they said it was 0.4% with substitution bias. That is, we gave you this and you can do better, and you could do better by 0.4%, okay? And 0.7% was because of new goods, okay? So what's new goods? The issue with new goods is when you do this procedure, you never allow a new good in the market. Is that clear? You're just following old goods over time and seeing how their price change. Is that clear? So a new good comes in, and it is eventually evaluated, but just relative to its earlier price and never relative to the other goods in the market. Okay? So you would assume that the new good came in, and some people enjoyed it, bought it at that price because it was better than the other things in the market. Okay? So there was a bias that way. Okay. So they did a couple of things. One is faster sample rotation. I'm not going to go over that. And then they did something else. They said, look, they didn't say it this way, but I'm going to say it this way. Okay. Maybe we can't account for new goods. Okay. But there's another problem that's very much related to this that we can account for using the characteristic space models. What's that problem? Okay. What happens when these numerators go to stores, okay, is sometimes they don't find the good on the shelves in the second time. Okay? You went to this store, you wrote down the characteristics of the good, okay? You went back to the store 2 months later. By the way, it's 2 months in everywhere except for LA, New York, and Chicago, where it's 1 month, the intervals, okay? But it's 2 month period. You go back, and it just isn't on the shelf anymore. So they just drop that good. Is that clear? Okay. So what's the bias? The bias is the goods that aren't on the shelf anymore are disproportionately the goods whose characteristics were obsoleted. So, what computers are taken off the shelf? When the Pentium comes on, the 431 chip goes away. Okay? So, and presumably those characteristics have been they've been obsoleted. That's part of the reason they're taken off the store. So when we look at price changes and we throw out those whose price changes have fallen, you're getting a bias positively. Is that clear? So one of the answers and at the BLS before I ever got there was, here's what we're going to do. Okay, what we're going to do is we're going to say we're going to do a regression function for price on characteristics. Okay, and then when the good isn't on the shelf in the second period, okay, we're going to evaluate what those characteristics would have been priced at in the second period. Okay, and we're going to use, instead of throwing out the ratio, we're going to use the price relative from those goods. Okay? Okay. In truth, as long as there was a good like the other good around in the second period, this satisfies Conus bound. Okay, because people could have bought it, okay, and they could have bought it at this price. So the big benefit of this is it partially controls for the sample selection problem, but you have to understand what it actually does and how you interpret it. Okay, so I'm going to get to that. So what match models things do, the problem with them, they don't use them anymore. I mean, they do use them for some things, okay, and they try not to. What they do is they generate a selection problem by throwing out goods whose characteristics have been obsoleted relative to other goods, or disproportionately goods that are characteristics have been obsoleted. What the hedonic does is it allows you to correct for the observable characteristics that have been obsoleted, but not necessarily for the unobservable characteristics that have been obsoleted, because you can't condition on that. Okay. Just before I go into the thing, you should realize they're doing this, but they're still missing stuff, right? Because the easiest way to think of the gains from new goods is the following, okay? It's that, say the price comes in very high and then typically falls. This is typically true of technology goods. By the way, they come in at a very high price. Not all goods come in at a very high price and then fall, but technology goods do. There's some goods that come in at an introductory price to get people to try them, okay? But if that's true, then at the highest price, what you're missing is the inframarginal rents of those who had bought it yet at a higher price. Because you'll never get that. Is that clear? You can never sweep that out because you don't have a price higher than that to find out what their real utility was. You know it's higher than the price that they bought at, but you don't know any more than that, okay? So you're going to miss that, okay, the inframarginal rent. But then what you will get is you will get the fall in the benefit of the fall in price thereafter, okay? And the fall in price, by the way, is not only the fall in price of this good, but because this good came in, other goods which are competing with it will fall in price too, and you'll get those too. Okay? So the advantage of the hedonic, okay, is that you're going to pick up the falls in prices of the goods that dropped out. Okay? And okay, fine. Okay, so let me go on. Okay. Now, to figure out what you're doing and how you can use it and how you can't use it, okay, I'm going to estimate price on characteristics. That's a hedonic function. I have to figure out what am I doing. Okay, what am I actually estimating and where does it work, okay? So these are the important details which I skipped, and I'll show you why they're important, and this is why it started to work, okay? So I'm going to use, let me take the same Nash-Bertrand pricing model that we think works pretty well, okay? And I'm going to assume single product terms. So price equals marginal cost plus the markup term, the semi-elasticity of demand, okay? So what's a hedonic equation? A hedonic equation is the expectation of price given own product characteristics. That's what you're doing. You're guessing price on own product characteristics. Okay, I'm going to get the coefficients and predict the price for the good that dropped out. Okay, so that actually is the sum of two regressions. It's the sum of marginal cost of the characteristics plus the sum of the markup against the characteristics. Everybody with me? Okay. So this expectation is over the distribution of other products characteristics. Okay. So there are two important points to make from this equation, which somehow I haven't gotten through to the rest of the profession. This markup term, okay, it depends on the stuff that Aviv told you it depended upon. It depends on the other products that are competing with the good. Is that clear? And it depends on the distribution of demographics in the markets that I'm interested in. Okay? So if I go from period 1 to period 2, I should expect the markup change to differ because new products have entered and old products have exited. That's the whole problem. Is that clear? So this equation shouldn't be stable over time. Is that clear? And moreover, it shouldn't be stable across markets because the demographics are different in different markets. And the demographics help me determine what price I'm going to set. Okay? So, I mean, the easiest thing is the computer example, chip example again. You know, it's not that the utility necessarily of a Pentium, of a 400 series chip, okay, went down when the Pentium came in. It's just that there was something else, another alternative that was there that forced the price of the Pentium, of the 400 series chip to go down. Okay? So that's one lesson. If you're going to use this, okay, you have to do a different regression for each time period in each market. By the way, what they did at the BLS to make this happen, okay, is they gave the guys the enumerators when they realized what was going on. Okay, this is maybe my biggest contribution to economics, was they gave the enumerators handheld computers. So they got the data in the daytime, and they can download it onto a mainframe at night, and then you do the OLS equation to get the hedonic in real time, because they needed to put the thing out by the end of the month. Okay, so this simple thing of giving this changed the way they did the CPI. Okay, so that's one thing. The second lesson to learn from this, okay, so which is the one that I think got missed, is the regression coefficients have no interpretation in themselves. They're not cost function parameters because they're mixed with markup parameters. Is that clear? And they were never intended to be utility parameters. Okay, only indirectly through the demand surface. Okay, so you cannot interpret the coefficient of a particular x to anything. You know, so if an x goes up a little bit, it doesn't mean that the value of that characteristic is much. So my favorite paper on this is a paper by Ian Coburn. Okay, Ian Coburn studied these drugs. So rheumatoid arthritis. I don't know whether I told this in class, but rheumatoid arthritis is it's a debilitating disease. You get sicker and sicker, and it's really a problem. And the National Institute of Health found this means you had to go to the hospital and stay in the hospital for a few months to get rid of it. Okay, it was really very serious, and one drug didn't. Okay, but the benefits of the two drugs, they're statistically independent. So both of them didn't work on some people. Okay. And if it didn't work on this person, it didn't matter. You had an equal chance of it working on the second one. So the response of the industry, of the drug industry to this was very clear. A bunch of people ran in, a bunch of companies ran in to produce drugs of the first type that didn't have any serious side effects. Is that clear? Prices of those drugs went down dramatically because everybody came in. It was a whole generation of drugs. They came in. The other group, okay, there just wasn't enough demand to support a lot of goods, and there was essentially a monopoly provider. I forget which firm it was, but there was a monopoly provider. So the price of the good that had the serious side effects was much higher than the price of the good that didn't have serious side effects. And so, Ian did this hedonic regression, and it said price people like, if you believe the coefficients in hedonics, is that clear? To be interpretive of how much you value characteristics. People like being seriously ill because the price of the seriously ill one was much higher than the price of the other one, okay? So it's a cautionary tale, but it tells you don't really want to interpret hedonic equations, okay, without knowing the system that's generating the prices underneath them, okay? So, it's the same when you value amenities and when you value anything else, okay? The question is, if you're getting it from prices rather than from a direct survey, okay, which often it is, you have to figure out what the pricing equation is, okay? And then you figure out what the interpretation of the coefficient is. Okay. So the two things I hope you learned from this is any procedure which requires the assumption that the hedonic function is stable across time or market is likely to be problematic, especially in fast-moving markets, okay, like computers, okay? And any procedure which requires an interpretation of individual hedonic equations, coefficients of those equations, So it's okay, you got the right prediction for price. You just don't have the right coefficient estimates. Or you got close to the right prediction for price. We know our R-squareds on that, I'll show you one in a minute, okay, are very high. So you got close to the right prediction for price. But interpreting any single coefficient is wrong. Okay? Okay. So let me show you a few numbers. You showed numbers. So these are computers, and then I'll show you two sets of numbers, and I'll go over them just a little bit. So this is from this paper by Tim Erickson and myself. So this is computers. These numbers aren't from the BLS's own data set, but they match up almost identically to the BLS own data set. Okay? These are the number of observations in 1995, 96, 97. That's the first row. The second row tells you how many of the 1995 observations were matched to the 1996 observations. Is that clear? So there's 44 matched to the 1996 observations. So you're throwing out 220 out of the 264 observations. Right? So if you think about selection biases, this is big time. Okay? This is not a little bit of biases. Okay? This is for a year thing. If you did it for every 2-month period, it's 20% of the products are not on the shelf again 2 months later. Okay? You can see what's going on. It's clearly all the products, the megahertz is going out, the megabytes are going up, the gigabytes are going up. All the products are increasing over time. And what's dropping out of this is the products that got obsoleted. If you look at table number 2, these are the various indexes. What's interesting is you use the hedonics, and you get these price falls. You actually get price falls for computers, which makes some sense. Okay? And you get them, from 10% to 30%. If you use the match model, you get price rises. Okay? If you actually did this, you get price rises. The reason you get price rises, you get price rises more in the periods when the price is falling more dramatically. And what's going on? The only goods that go over the 2 years are the high-quality goods that came in a little early. And their prices don't fall. So the years when when a Pentium chip came in, all the 400 chips went out. The only chips that stuck around were the Pentium chips that were put in just before the month before it. Okay, and their prices didn't fall. Okay, so when the Pentium came in, which was 97, 98, you actually got an increase. Okay, in the computer thing. Okay. You can do this many different ways. I want to just show you one, just to be careful. This is the only thing. I want to show you one thing just to make you a little bit careful. So the thing about computers that's useful is the characteristics of computers are mostly observable. The things you care about are things like megahertz, megabytes, RAM, maybe the screen, the resolution of the screen. Okay? But many products have unobservable characteristics, okay? Including, certainly serials and including TVs, okay? So I'll show you just the importance of this, okay? The TV, so now I'm using exactly the BLS data. This is the data that is used to compute the TV index, okay? Tim Erickson, the co-author on this paper, is the head research guy at the BLS. Okay? So we could use their data. Okay. So most of the TV, unlike computers, most of the TV characteristics are dummy variables, which are 1 or 0. Is that clear? Okay. So you had flat screen, plasma, picture-in-picture. There were like 10 of them, and they were all high-end things. Okay. And what happened in this industry, okay, is the exit wasn't at the low end. The low end, there were always these black and white TVs that sold for $80 or $100, okay? All the movement was in the upper end, okay? It was we were replacing flat screen TVs with other flat screen TVs with more pixels per inch and more this per inch, and the picture-in-picture was sharper and everything else, okay? So it works out that in TVs, most of the important characteristics of the things that were exiting, we couldn't control for, okay? Indeed, after the Boston Commission, there was a National Academy Commission on the price index problem because they were worried about the deficit stuff. By the way, what happened at the end with Greenspan is, actually, I should stop stories, but what happened at the end with Greenspan is that the budget deficit, you guys probably don't remember this, but it eventually got resolved. And once the budget deficit got resolved, everybody forgot about the CPI. So maybe they'll get to it again now, but for the last 10 years, nobody's done anything on this, except for a few of us have written papers on, which tells you something about the political system. Okay, so what happens in TVs is the exit is disproportionately of high quality goods that are replacing other high quality, and they're yet more high quality, but we don't have in the data set the number of pixels and things like that. Okay? They just aren't in the data set, so we can't condition on. So they go into the residual, and as a result, the TV market selection is largely based on these unobservables. Okay? So when the National Academy of Science, whose members all of you have heard of because they're all famous economists, okay, came and they said, okay, we know you were right on computers, okay, but we're now going to choose some other things, among them TVs, and we're going to do a hedonic versus a match model, okay, and we're going to see what happens, and this is what they got. This is not what they got. This is what I got when I recomputed what they got, okay. But you can see the match model index fell by 10.1% a year when I had actually 24 characteristics, which is a lot of characteristics, okay? And the hedonic fell by 2.1% a year, which isn't very different. Is that clear? And indeed, you could never do a hedonic every period with 24 characteristics. There's too much cleaning that needs to be done. Just the data analysis is too much. So you would end up doing it with 8 characteristics or something like that, 9, I guess. And there you see the rate of fall of the hedonic is even less than the match model, okay? Which is exactly the opposite of what we got on computers, right? So the economics of the selection problem are still there and still in force, okay? What's going on is that the match model index, okay, it only corrects for the falls in prices of continuing goods, but it corrects for the fall in price also of the unobserved characteristics of the continuing goods. Okay? And the hedonic corrects for everybody, but just on basis of observed characteristics. And what was going on in this market was it was the unobserved characteristics that were throwing out everybody. Okay, so you have to be careful when you're doing this kind of stuff. Okay? Let me just say, if you did the regression function on just 9 variables, just to show you, I'm now just summing up, okay? The paper goes on to show you how to condition also on unobservable characteristics, but it's not for this seminar. We're doing demand systems here. But what I wanted to say to you is these are the R-squareds from regressions on the monthly data. These are actual data regressions on the monthly data at the BLS on 5 characteristics, 10 characteristics, and 24 characteristics. Okay? And this is without putting in all the markup term stuff. So it's just price against X. I said it was a good prediction. Okay? These are real numbers. Okay? So the minimum over the 36 months in the sample or whatever it was 0.896 with 5 characteristics and went up to 0.96, the R squared. That's the minimum R squared. okay? And to that, you're going to add the markup term, which always makes sense. I mean, just the intuition of it makes sense, and it does make sense. Okay? So you're going to get, these data are better than the data we usually use, okay? They're just better. So you're going to have noisier data. It's going to be a little less, okay? But the pricing equation, if you put in the Bertrand-Nash type pricing equation, are going to give you R-squares on the order of 0.9, okay? Almost always, okay? So it may be wrong, okay? But it's a good place to start, okay? To think about this problem.